And welcome to your lab over single photon interference. And what we're doing in this lab is basically demonstrating the Young experiment. And what this experiment showed is whenever you send particles, in this case photons, through a double slit, we get an interference pattern contrary to what we might expect. So let's draw this picture of what we thought might have happened, or what you might expect to happen intuitively, and what we actually see. So anytime we shoot a photon, a single photon, just one photon, right, through a double slit, what you might expect to see some distance away on a shield is photons coming and striking this side in two groups, right? Like pouring sand through two slits. You would expect just two piles of particles that are coming and striking our detector some distance away. However, what we end up seeing, so let's redraw our picture here. After we shoot a photon, is that photon will actually interact with itself, and on this far screen, what we see is an interference pattern where we have some central area, very high intensity, where it means it's being struck by a very large number of photons. And then to either side of that, we have two other areas, which might have a little bit fewer photons striking. And then as we go off, we can have some other areas which have even fewer, okay? And so we call this is our diffraction or interference pattern. And this happens when we only send a single photon through, okay? And so if we were to graph the intensity or the number of counts versus the position, this graph might look something like this with a series of peaks. And the intensity of these peaks increases as we hit each one of those bumps, okay? And so we have an equation that relates the wavelength of the photons that we're sending through these two slits to the slit width. So this slits are going to have some distance apart from each other, and to the angle at which it strikes our detector some distance away. So we measure the distance or the angle between wherever the position of our central maximum is to wherever the position of whichever diffraction order that we're looking at, and that's our angle theta. And so the equation that relates all of these things is going to be m, which denotes the diffraction order that we're talking about, lambda, which is our wavelength, d, our slit distance, and sine theta. And this is our diffraction equation that we're going to be confirming and using in this lab in order to determine what the wavelength of our photons are, okay? And so let's talk about this diffraction order a little bit more. This central maximum we call m equals 0. And then we'll have on one side increasing diffraction orders, 1, 2, 3, and so on. And then on the other side, we'll have our negative diffraction orders. These will be symmetric. So this is just an index that lets us know which peak on this diffraction pattern am I talking about, or which peak on this interference picture am I talking about. Okay, so it's a way of indexing which peak you're looking at. Okay, now it's going to be difficult for us to be able to measure this angle theta to where we're going to be able to see these different, or where we'll be able to find these different peaks. So what we have to do instead is use the geometry of our system and rewrite this equation in terms of things that we can measure. Okay, now it turns out for a small angle approximation, the sine of theta is approximately equal to the tangent of theta. So we can rewrite this equation for diffraction for a small angle theta, which is what we're going to be using, as d tan theta. And tan theta is going to be the opposite side, so we'll label this distance here, which is the distance from our viewing, or from where our detector is to our slit. That distance we'll label L. And the distance from our central maxima to wherever our diffraction order that we're looking at is, that's going to be a distance d. Okay, so we can rewrite tangent of theta as capital D over L. And from this, we'll get the final equation that we're looking for, which is going to be d, so we're just going to rearrange this in a convenient way, is equal to m lambda L over D. Now L and little d, where d is again the separation distance and L is this distance from the detector to where our slits are, those are going to be constants, so we don't have to worry about those changing. What will change is the position of these peaks, so depending on which diffraction order we're looking at, we will have a different distance to that particular diffraction order from our central maximum. Okay, so if we can measure these different distances at different diffraction orders, we'll then be able to experimentally determine lambda by looking at the slope of our graph. So let's look at that graph and what it might look like. We're going to graph m on our x-axis. So m is our x, d is going to be our y. So on our y-axis, we're graphing d. And so for each of these diffraction orders, so for 1, 2, 3, and -1, -2, and -3, we'll be able to measure this distance from the central maximum to that diffraction order. So we'll have a different displacement for each one of these different diffraction orders. And so, it's a bad picture, but this should be a straight line with these data points aligning on that line. Okay, and the slope of this line is going to be, right, this term here, what's left over, this is our m, or our slope. So it's going to be lambda L over d. And so we can use, once we find the slope of this line, we can then find the wavelength by just taking that slope and then plugging it into this equation here and then solving for lambda. Okay, so that's simple enough, but now how are we going to go about finding these distances? Okay, so that's what the whole point of this lab is to be able to make a graph that looks something like this and find the positions of each of these diffraction orders. And then from those positions, we can then make our graph here and then get the wavelength. So to do that, what we're going to do is we're going to have a slit that we can use to block off all of the light except for a very narrow region. Okay, so this slit might look something like this. So it's blocking out all of the photons that are coming from here, except for the ones that can make it through this narrow slit. And then we'll get to count the number of photons that make it through that narrow slit. And that'll give us a count at that position on this screen. And then we'll take this slit and we'll move it over some, and then we'll take another count and we'll be able to count the number of photons at some other position on the surface of this screen. And so eventually, if we take a good enough resolution, we'll get a graph that looks something like this, right, with different counts at different points that we've looked at. So we just filter out everything except for a very small portion of the light that's going to be hitting our detector. And then we take a count, and then we just move the slit over, and we take another count, and then you'll build up a graph that looks something like this. And then from the position of these peaks, you'll be able to determine these displacements d, and then you'll be able to make this graph. Now, how are we going to be able to count the number of photons that is striking a single point? Well, that's where what's called a PMT comes in. This is the photomultiplier tube. Okay, and basically what it is just a series of very closely spaced charged plates, and we're going to have a very high voltage applied to these plates, in our case 900 volts. And so what happens is whenever a photon comes and strikes this PMT somewhere, it's going to dislodge an electron, and that electron is going to again be accelerated and hit the next plate. And whenever it hits that next plate, it's going to have so much energy that it can then excite two electrons. And then those two electrons get further excited, and they both excite two more. And those two can then excite two more. And you get this cascading effect. So what was a single photon now becomes this cascade, or this series of electrons. So what we have a small signal over here gets converted into a large signal down here that we can then count. And so for every one photon that we see coming and striking our PMT, we'll be able to measure a large signal over here, and we can get a number of photons striking any given position on the surface of this PMT. And that's how we're going to be able to get counts at different positions along the surface of our detector here. Okay, so that's basically it. So the math isn't too difficult in this one, right? It's just really just this equation. We just did a little bit of algebra and used a little geometry to get it into a simpler form. And then from this, like I said, we're going to use this, we're going to be able to see that this diffraction pattern is created by just sending single photons. And then from that diffraction pattern, we're going to solve for the wavelength of the light. All right, so what we'll see next is a demonstration of the instrumentation. We'll go through how you would have calibrated it and then recorded your counts at different positions on the surface of this PMT. Okay guys, this is going to be the setup for the single photon interference. So if we come down here and look at what's going on inside of this enclosure, this is going to be our photon it's our photon gun. So this is going to send out individual photons, so it's a very low intensity green light. Here we have a laser that we're going to use to align all of our optics. So it's actually already aligned, but we'll go in and show you how this was aligned. So we have to adjust the laser so that it passes through this single slit here, and from there we can check to make sure it's going through that slit by putting our screen. And on our screen you can see that we have some interference pattern, but the purpose of this slit is just to align the laser so that it's going down the center of this enclosure. What the important part, or the part that we're going to be focusing on more, is going to be down here. So this is going to be the double slit assembly. So here we have a double slit, and then on the other side of it we have a single slit that we can move in order to block it. So if we turn this micrometer here, you can see that it changes the position of that single slit, so that if the single slit is overlapping these two slits, then it allows light to pass through both slits, and then it comes out and travels down the rest of our enclosure here. Okay, so this is a way that we can control whether light is going through one, two, or none of the slits. So to check this in a very rough way, we're going to start with it blocking this beam. Let's move our screen down here. Okay, and then as we rotate this, we should see a single strip of light begin to form. Here it comes. All right, so there's with one slit open. Now if we continue to rotate this, it's going to allow light to pass through the other strip. There we go. You can see that it's brighter there. And then as we continue to rotate this, it's going to block one of the slits. So there we go, we're back to one slit. And as we continue, it's going to turn off the light because now it's blocking the light that's passing through both of these slits. Okay. So this is a way of controlling the amount of light that's passing through the slits. So we want to find out what position do we need to set this micrometer at such that it's allowing the maximum amount of light through. And to do that, we have to use our oscilloscope. So we're going to go ahead and pop the top back on this guy. We have to latch it down using these guys here on either end. All right, and so we will start with the light, with the micrometer all the way in, right? And as we turn it, we can look at the voltage on our oscilloscope. And so as the light is passing down here, it's going to hit a photodiode, okay? And this photodiode, if we look at the back of what's going on here, you can see that there's the output for the photodiode. It's coming all the way over and to our oscilloscope. So the amount of light that's striking that photodiode will produce a higher voltage. So we're going to turn our knob until we see that voltage start to go up. And I'm turning the wrong direction. We're coming back. Let's come the other way. All right, you can see it's starting to come up. So there, you can see I'm turning it, but it's staying constant. That's with one slit being open. So if I continue to turn it now, there we go. It's going to come up. So now both slits are open. And if I continue to move the position of that single slit, we're going to come back down so where only one is being open. And then if I continue to turn this, it'll turn off. Okay? So we need to mark the position where it goes from one slit to two slits. So we need to come here, take down this position here, and then we're going to go the other way. So from 2 slit to 1 slit there, and we would mark down that position. And if we take the average of those two positions, so it'll give us the point where the most light is passing through both of our slits, and that's going to be the ideal position for this here, for this single slit, because we want it to pass through both slits so we get that interference pattern. All right, so that's how we would align it. So what I'm going to do now is we're going to get the whole system set up so that we can start to take counts, and I will be right back and we'll show you what that setup looks like. Okay guys, we got our setup for the PMT ready now, so we're ready to start taking some counts. But before you do that, let's look at our setup here. So this is going to be our counter, and you can see that if we look underneath here, this is going to our monitor. So this is going to channel 2 of, this one here is going to channel 2 of our oscilloscope, and this other one, the input, is going to the back of our PMT. So anytime we get a count from the PMT, it's going to get sent both to our oscilloscope so we can see it, and to our counter so we can count it. Okay, so what we first have to do before we start counting is we have to push the laser out of the way, because right now the laser is going to block this low intensity light. So we can actually just slide it over. It's magnetic, so we just push it over. So now it's not blocking the light, and we can put our top back on. So we'll put the top back on, make sure everything is locked down so no light can get in. And it's very important that whenever we are using the PMT, that everything is very locked down and secure, and that we're not shining the laser, because the PMT is very, very sensitive and it's very easy to damage it. Okay. All right, so now we're going to come over here. We're going to turn our bulb on, so we're going to flip that down, and we want the bulb power to be at 5. So we turn our bulb power to 5. There we go. So now we are currently sending photons down the length of our tube. And now let's come down here and set this up so that we can count them. All right, so first thing that we need to do is apply a voltage across our PMT. So let's go ahead and first turn the PMT on. You can see I have this multimeter set up so that we can measure the voltage that we're supplying to the PMT here. All right, so we want to supply 900 volts. So I'm going to turn this knob up here until our multimeter reads 0.9 volts. It steps down the voltage, because obviously we can't get a multimeter that can read 900 volts. So it steps it down. So even though we're supplying 900 volts, it divides it by 1,000, so we're looking for only 0.9 volts here. So when our multimeter reads 0.9, that means we are now supplying 900 volts across our PMT. Okay, now we can go ahead and open our PMT up. So this is a little shutter that's currently protecting the PMT. We're now ready to start taking measurements, so we're going to open that up. And if we come down here and we look at our counter, right, we can see that it's set to be a timer for 10 seconds. So if we flip this up, it's going to start taking counts. And it's going to take it for 10 seconds, and then it's going to switch itself off and pause momentarily so you can record that data, and then it's going to restart its count after that. So you got to be quick whenever you're taking your counts on this. So let's go ahead and turn that off for now. Let's go ahead and look at what's going on our oscilloscope. Okay, so we're just going to follow the instructions exactly like it says in our manual. So we're just going to set channel 1 to 200 millivolts, channel 2 same way, the divisions to 200 millivolts, so we can change the divisions on our scale by changing here. And you can see down here both of our divisions are set to, well, now they're both set to 200 millivolts. We're going to come to our trigger menu, set the trigger to channel 2, and set the trigger level to 200. Okay. Now what we want to do is change our horizontal divisions so we can actually see what's happening here. Okay, and so what we're viewing here in channel 1, this color here, these things that are jumping up and down, those are the signal that is coming from the PMT, and then that signal gets converted into a signal that we count, and that's what you're seeing on channel 2 here. So for every one of these signals that it gets, it sends one of these signals to the counter and counts it. Okay, but you can see that the amplitude of these is kind of crazy, right? It's counting very small noise oscillations and very large oscillations that are corresponding to photons hitting the PMT. So what we need to do is change the discriminator voltage on our counter so that it says, okay, if these incoming signals are not above a certain level, we're not going to count it. Okay, and we want to change that until our frequency is about half of what it is now. So this is the number of counts that we're getting per second right here. And so we're going to change our discriminator voltage. And what you'll see as I change this discriminator voltage is you'll see these oscillations become much less apparent. So we'll be counting only the large ones and not the small ones. And then we want to increase it until our frequency is half. So we do that by coming over here, and we're going to turn up this knob. So I'm going to turn this knob here, and that increases the discriminator voltage, right? And as I turn that, we're going to see what happens on the oscilloscope here. So let's go. So it was at about 6.4 before, so we wanted to get it to about 3.2. So I'm just turning that knob, increasing the discriminator voltage, and you see those oscillations are starting to go down, right? So now we're only counting those larger amplitude signals. We're kind of filtering out the noise. Okay, so that's good enough. Let's just leave it there. So now we're ready to start taking measurements. And to do that, we're going to just set this to some initial, right? Because this determines the position on the PMT that we're taking account from. So if we set this to 0 initially, we're going to keep on going in. So now we're set to 0. Right, we can take a count with that set to 0 now. Actually, before we do that, what we need to do now is take a background count. So we're going to actually close this, right, and we're going to take a count of background. And so this is just from the noise, right? It's because we closed that, we know that these counts are not coming from the photons that are striking the PMT. So this is why we take a background. And then we're going to subtract this background from each of our measurements each time. So that background was around 30. Let's let it go up again and see if it's about the same. It should be. It won't be exactly the same each time. There we go. So that time we got 42 counts, okay? So each time that we take a measurement, we want to make sure that we're subtracting this background, and that background will be included on your data sheet. So you don't have to worry about recording that right at this second. Okay, so let's turn that off. Make sure that we're set to the right position. Go ahead and open up the PMT. So now we're going to be counting the number of photons hitting the PMT at location 0. And then we're going to take a count. All right, so that's our count for position 0. We can go ahead and switch that off. And then we would just come over here and change the position. I don't remember exactly how much it wants you to change it, but let's say it said increase it now by, let's say to like 45, right? Let's increase it by that much, right? Just arbitrarily. But in your data, right, it would say, okay, increase this by a certain amount each time. So we're just moving that slide across the PMT here by a set amount each time, and then taking a count at each position. So let's just take another count as an example. This will be the last one, but I think you should get the idea by now how this works. All right, so at this position, we would record this number of counts, right? And then we would just come over here, turn this by some set amount, come back over here, hit that, and take another count, and then you just repeat, right? And so that is how this lab works. So hopefully that demonstrated well how you would go about getting your counts and how you would align this whole system, and how you set your discriminator voltage so we're not counting noise, right? So all of those things are very important. So yeah, so take that, you take that and use the data that's included on Canvas, and you should be able to now complete your lab report. All right, guys, we'll see you next week.